And we've actually seen, you're losing due to fuel, you're losing some of that, so we've actually kind of already done some of that lecture for section 9. And I will tell you guys, for the final, there won't be anything from 15.9 on the final. That's okay, just so when you're studying or preparing for the final, that's that variable mass problem. It's an optional section in the book, and so I'm gonna have to do some homework problems because I think they're important, particularly for folks that are gonna be dealing with so if you're doing calculations for like fluid catalytic crackers, if you're even into chemical engineering and you're doing any kind of solids transfer, you need to know those delta M's pieces for dynamics. So that's why I wanted to make sure you guys got those problems, because those were always problems when we were dealing with loading catalyst bins, taking care of flow bins around. Those questions actually popped up, and having dealt with it in real world situations, not necessarily in what you normally think of. For example, when you're dealing with waste, if you're doing civil engineering type work and you're doing dumps of gravel, you may end up having to deal with those kind of calculations because those are significant. And I didn't want to, and I knew background of where some of you are heading, I wanted you to actually see those kinds of calculations. But I'm not going to test over those. Now, there is one on the quiz, but I'm not going to do one on the final. Okay? So, just kind of giving you a heads up on that. Okay. So here we go. I did get the lecture posted yesterday, so we're good there. I got it posted this morning. So we've got that. I've got the recording starting now, so we're doing good there. And so now we're going to start talking about collisions, even though we already started talking about collisions. But we're going to go into it a little bit more than what we have done in the past. So when we do it in physics, and you see it in physics, we talked about the fact that collisions can be either elastic or inelastic. And we've done that from a variety of different ways. When we did collisions back in engineering physics, you usually start with another billiard ball. And depending on what's happening, we look at the collision before. So if I have my start here, this is my before, so I have an initial velocity. This has an initial velocity of 0. And if things are working out okay, usually what happens is this is going to go off at the new velocity. If it's perfect, this would be 0, but this might dribble off, and this is off at a bigger angle. We also did things like I could have a collision with 2 objects, and these would bounce off. When we had things like an explosion with pieces that would bounce off in various areas. And so those were the kinds of collisions that we have kind of previously worked with and dealt with. Well, when we start looking at real objects, so we're still going to start with our billiard ball. And we know with my billiard ball or my pool cue that this is the center of mass, right? And we follow the motion associated with the center of mass. Now, one of the things that was, as we're working in this particular chapter, and as we start going into rigid, when we hit chapter 16, we're going to start looking at things as rigid bodies. Right now, we're treating things as particles. And as we treat this as a particle, I don't have to worry about the motion of my ball. Because what we know really is, in real life is happening is that ball is rotating, right? But if I'm doing it as a particle, I'm only worried about how the translation of that center of mass is going. So I'm actually just looking at it from that perspective. So what we end up doing is we actually look at collisions a little differently now. So as my ball comes in to hit the other ball, we're following it via the center of mass. We're going to use this as called the plane of contact. Okay, that's the plane of contact. We can have two types of collisions relative to the plane of contact. One is my center of mass is going to act along this line, and this is called the line of impact. And if my motion is happening along this line, this is called a central impact. So we're going to deal with something that's called a central impact. And that's when the motion of the particle in the center of mass makes the motion of the particle is when the direction of motion of the centers of mass is along the line passing through the center of mass. So that's going to get me our central type of a collision. I can have a different one. This is still my plane of contact, except now my center of mass may be hitting towards that, and it's making an angle with this line of impact. And this is considered an oblique. So we have a little bit more of things that are happening than what we're used to. You know, we just dealt with conservation of motion, we did just elastic and inelastic collisions, life was a little straightforward, and we have conservation of momentum, and we're okay. But now we're starting to take into account what really, really happens. And if I can get to it, I want to find some slow motion video to actually look at how this is working. So let's look at the stages of a collision. So I've got stages of a collision. So at first, let's take our billiard balls, and we're going to do it. This is going to be traveling with an initial velocity for ball A. And this one's traveling at an initial velocity for ball B. The thing here is we're going to say that the initial velocity for ball A is greater than the initial velocity for ball B, so that we know that a collision is going to happen. Okay? At the impact, we're going to get an impulse from A onto B, or 1 onto 2. And we know that impulse, and for right now what we're going to do is we're going to relate it to our P dt. And this is A on B. I have an equal but opposite reaction, so I'm going to end up with a negative PD. So frame of reference becomes important. No, this is impact. This is impulse. So it's going to be the force. It's a force. We're going to use P and R partially because this is what we're going to call, this is okay? Because right now the particles are going to hit, and we know what happens because we've seen slow motion cameras of what happens. My balls will kind of squash, you know, they'll kind of squash together, and this is the maximum deformation. And this is kind of that instant at 3, the stage of the collision that I'm in. And that's my maximum. But then we know what happens next. The balls are actually going to come together, and normally what we think of is they're going to split apart. but I get what we call the recoil, or what the book calls the restitution phase of the collision. And in that case, I'm going to have an r dt, and then I'm going to have a negative r dt. So this is just before, this is just after. And we end up looking at our collision through all of these phases. And then finally, at the after, I end up with my balls going off, except this time, this ball, this is B after, and this is VA after. The velocity of BA is going to be greater than the velocity of AA due to conservation of momentum. So we can look at through the stages of the collision. And much like we looked at other things, so let's kind of think through some collisions here before we dive in. Remember, I had, or almost everybody, doesn't matter whether you took physics from me or you took physics from somebody else, I've got a bullet, my bullet hits the pendulum, right? And my bullet ends up as part of the pendulum. Okay? So if I'm looking at this as the before, we know we have the mass of the bullet, the velocity of the bullet, plus the mass of the target, plus times the velocity of the target. And usually in my ballistic pendulum, we're starting with this being 0, so I'm only dealing with my mass of the bullet. Then afterwards, we end up with the mass of the bullet, velocity after. And then, because this is a ballistic pendulum, we also look at what happens after. And usually what happens after in our ballistic pendulum is we're dealing with this portion of the collision. So we start down here with kinetic energy, T, right? And we go up here to potential energy, and we know those are equal, and we can either figure out the height, or we can figure out the velocity, or vice versa. But we look at our collisions in different stages. When we're working these problems, we're breaking up the system to look at the collisions in different stages. We're going to do the same thing to work a lot of the problems going forward. We're actually going to break it up and look at the different stages. So as we start thinking about that, we want to look at it. So, yeah. Hard to see the bottom. Let's see. Let me try it. How's that? That's better. Okay. All right. So, let's look at what we've got from a theory point of view. So I have mass 1, velocity 1, plus mass 2, velocity 2 is equal to mass 1, velocity 1 after, plus mass 2, velocity 2 after. And that's kind of in our situation where we had the collision and we've got our two balls that are going off in that direction.
Would mass not change at all?
Correct?
So like can you just get rid of the m's and just
Not necessarily. They may not be the same mass.
Okay.
And, you know, I don't know that those two masses are the same or different.
But aren't all billiard balls the same size?
Not necessarily. Well, billiard balls, yes, but cue balls and pool balls are not. The cue ball has a slightly different mass than the rest of the balls.
I did not know that.
Yeah. You know, but in this case, this is our most general form, right? We don't necessarily know that the masses are different or the same.
What if it's not full? What if it's
Well, in this case, like I said, this is generalized. Because right now we're doing theory, okay? So now we have done our work, our impulse momentum, right? So I've got my initial minus, now I'm going to have that impulse that occurred is going to equal mass 1, V at the deformation stage. So really what we're looking at here is this stage of the collision. So when I write this equation, that's the stage of collision I'm at. Right? This is conservation of momentum. And this is kind of our impulse equation that we've been working with. Okay? I can now look at, so this is at the deformation stage, so now let's look at it at the recoil stage. Or restitution stage. This V and that V are really the same. Because this becomes the initial one for this phase, this becomes the final one for that phase. And the reason we do this is because we want to look and define a ratio. And we're going to call this ratio E. Okay? We're going to define this ratio between the two impulses. Essentially what this E does is this E is going to tell us how elastic the collision is. So essentially it's going to give us a measure of, are we completely inelastic or are we completely elastic? It's going to give us that measure that's going to let us do that. So basically what happens is this. E is going to be defined just like that. So this is the restitution phase, and this is the deformation phase. So for mass 1, I'm going to end up with E being V minus V1 after, divided by V1, which is my initial, divided by V. I can come up with it similarly for mass 2, and things are a little just backwards. And I can actually look at how this is. So if E is equal to 1, it's a totally elastic collision. If E is equal to 0, it's a totally inelastic collision.
So it would be impossible to gain, to be greater than 1.
Yeah. So it's a totally elastic collision or a totally inelastic collision.
So for the V for mass 1, is that the same as the V for mass 2?
This V, it depends on, yeah, you're in and up. But this is our V for mass 1. Now, We also call these plastic collisions. Okay. And when this happens, the energy lost is at its maximum.
What's like a real life example of that?
That ballistic pendulum problem.
Cool. The ballistic pendulum, like where you.
This is a completely inelastic collision.
Oh, okay. Yeah, because you shoot the bullet in, and it doesn't move at all. It like
It's part of the new. It's all together.
Okay.
That's a completely inelastic collision.
Okay, understood.
Dropping a bowling ball on a cushion.
Not necessarily. That one may not be a completely inelastic collision.
It's one of those things that doesn't happen very often, does it?
What?
In real life.
Elastic collisions?
No, a completely inelastic collision.
Oh, it happens a lot. An
Okay.
arrow into a target.
Okay.
A bullet into a target.
Is there something that where like when it goes in, it just completely stops?
No, it just becomes part of it.
Okay.
It doesn't have to completely stop. Because we know in the ballistic pendulum problem, it doesn't completely stop initially, right? Ballistic pendulum problem, it travels partially through the way.
So a bullet bouncing off of Superman's chest would not be an inelastic collision.
That would not be a completely inelastic collision.
Okay.
Ice skaters coming together approaching each other and coming together and spinning together is an inelastic collision.
Okay.
Yeah, so we get those inelastic collisions. Now, remember what we're saying here is that the sum of the energies that come in, and this is related to kinetic energy, T1 and T2, in a totally inelastic collision, I get conservation of kinetic energy. Total inelastic collision, the energy loss is at its maximum.
Will there be any velocity change?
Oh yeah, you're always gonna have velocity change. Always have you will have a velocity change. Are we good over there? For those of you who are attending on the screen?
Yes.
Okay. All right, so let's look at some collisions to help work through some of this. So we're going to start with an example, and we're going to break it into parts because that's exactly what we want to do. So we've got a pan sitting on a spring. The pan has a mass of 10 kilograms. The spring has a spring constant of 20 kilonewtons per meter. I'm going to have a block that's on here, and it's going to be a 30 kilogram block. In this case, we are assuming a perfectly plastic or inelastic collision. Okay? And we want to know the maximum deflection of the spring. Okay? So we're going to have to break this problem up into parts. So we're going to want to look at before the collision. Before the collision, I'm going to have the weight of my 30 kilogram block. I'm going to have the weight of my pan. And if I do this, this works out to be 294.3 newtons. That one works out to be 98.1 newtons. So I have my weights of those. I'm going to have a deflection of the spring due to the pan. Okay, I'm going to have a deflection of the spring due to the pan. And that's going to be related to the weight, which is going to equal kx. So the weight divided by k is going to equal x. That's going to give me my 10. I happen to write it out this way. And this is my 20, 10 to the third. And I'm going to get x is going to be 4.91 times 10 to the minus 3 meters. So this is deflection due to the pan. I'm also going to have potential energy of the block. And that's going to be my 30 kilograms times gravity. And we're dropping it from a height, I just didn't write it down. We're dropping it at a height of 2 meters. And that's going to give me 5.88.6 joules. So that's before the collision, or at the start.
Contact.
This is at the start, okay? So now we want to look at the point of collision. So this part, we got the pan, we now have the block on the pan, I got my spring. We know that the potential energy of the block is now equal to the kinetic energy of the block. And that's going to give me my 1/2 mv squared is equal to mgh. Masses cancel, so v squared is equal to 2gh. V is equal to square root of 2gh. Gives me the velocity of the block is going to be 6.26 meters per second in the downward direction. So I've used conservation of energy to give me the velocity of the block. If it's a perfectly inelastic collision, I'm going to get the mass of the block times the velocity of the block is equal to the mass of the block plus the mass of the pan times the velocity nu. This is for a perfectly inelastic collision. I'm going to have those things there. So now I get the velocity nu is equal to mass of the block, velocity of the block divided by the mass block plus mass pan. It's going to be 36.26 divided by 40. It's going to give me 4.70 meters per second headed down. Now I can calculate the new kinetic energy, which is going to be 1/2 the total mass, which is 40, times my new velocity squared, and it gives me 441.8 joules. Everybody with me so far?
Yeah, good so far.
Okay. Now, maximum deflection. Okay, so this is at maximum deflection. All right. So this is start. This is the deflection due to the pan. And this is the deflection due to pan and block. Okay. We're going to call this X1. We're going to call this H. And we're going to X2. So X2 is going to equal H plus X1. All right. So, the potential energy at this point here, okay? The potential energy at this point here is going to equal the weight of the block plus the weight of the pan times H plus 1/2 kx2 squared. And you can look at this as minus h because we're below the point. So this goes back to our calculations of 294.3 plus 98.1 times minus h plus 1/2 kx2 squared. This is going to give me 392.4 h plus 1/2 kx squared. So I can look at the total energy before and the total energy after. So total energy before is going to be the kinetic energy at the top plus the potential energy due to the spring due to the pan, which is equal to the kinetic energy at the bottom plus the potential energy at H. This potential energy at the pan is going to be 1/2 my 20 times 10 to the third, 4.91 times 10 to the minus 3 squared, because that was my deflection just due to the pan. And that ends up being 0.241 joules. So this equation is going to end up looking like this. Kinetic energy at the top is right after, that's where that came from. The potential energy is going to be that right there. I'm at maximum deflection. And that's where I'm going to be at 0. Then I'm going to have my 392 minus h plus my 1/2 kx2 squared but h, recall, is x2 minus x1. So I can plug that in. So now I'm going to get 442 is equal to 392, and I have a minus here, and I get x2 minus 4.91 times 10 to the minus third plus 1/2 20 10 to the third x2 squared. At this point, you can solve for x2, and it turns out that that's 0.230 meters. Then I can solve for h, and that's 0.225 meters. So we have to break apart the problems to before, after, during to make sure we're accounting for everything. So let's look at a different problem. So I've got an inclined plane, and it's 30 degrees. I've got a little stop here, and I have a triangular block that's up the inclined plane. This block is going to be a 10 kilogram block, and I'm going to be sending in a 10-gram bullet. The velocity of this bullet is 300 meters per second. We know what's going to happen once the block gets hit on my inclined plane. It's going to move up the inclined plane. And we want to know the distance it moves up the plane. We're told that this is a smooth surface, and so we get to make the assumption that the force due to friction is equal to 0. So I don't have to account for friction. So what's going to happen then is draw our situation. The bullet's going to come in like this, but my motion is going to go like that. And we've done this before, so I want to look at what's happening from a geometry point of view. Okay? And my bullet's going to come in. I'm going to give myself a reference point. This is 30 degrees. And by experience, we know that this will be 30 degrees. Okay?
That side right there would be 60. 90 plus 30 would be 180.
Well, that'll be 60. We're not going to need it. Because what I want, I'll give myself some geometry here. What I want is the velocity perpendicular and the velocity parallel. And I'm given this velocity is 300 meters per second. So that means the velocity parallel then becomes v cosine 30 degrees. Okay, so you see why I did that? Because I need the velocity in the frame of reference that's going to make it easy on myself to do the problem. So now I'm going to have the mass of the bullet, the velocity of the bullet parallel to the plane is going to equal, this is an inelastic collision, so I get the mass of the bullet plus the mass of the target velocity along the plane. Okay? So now I just do my mass of the bullet, velocity parallel, divided by my mass total. That's going to be my, because it was a 10-gram bullet, I'm going to have my 300 cosine 30.01 kilograms. And that gives me 0.259 meters per second. And now this is going to work very similar to the ballistic pendulum problems that we've done in the past. Because now, conservation of energy, which gives me that the kinetic energy at the bottom, kinetic energy at the top, but we know that's 0 at the x we're trying to find. So this is going to give me 1/2 mg, or 1/2 mv squared is equal to mgh. Okay, this is the mass of the bullet, this is the mass total. And this right here assumes the following. Just like in my ballistic pendulum, this is h. So what's going to happen here is my block is going to slide up some distance d, but this is h. Okay? And that's 30 degrees. So if I look at this, the sine of 30 degrees is equal to h over d. D is the distance that we want, so that's going to be h divided by the sine of 30 degrees. And this h is going to come from that right there. So I'm going to end up with, that's not the mass of the bullet, sorry, this is the mass of the target plus the bullet. That's total, because we've calculated this afterwards. So I'm going to end up with what we've seen before. H is equal to 1/2 m total v squared divided by g mass total. This is 1/2, the masses total cancel out. This becomes 0.259 squared divided by 9.81. H works out to be 0.003, 0.003 meters. Plug that back into there, and D works out 8.4 meters, or 6.84 millimeters.
So it doesn't move a whole lot.
Doesn't move a whole lot.
6.84 is actually
That's millimeters.
Yeah, I know, but still, that's 1 millimeter is still 0 is nothing, but 1 millimeter is something. If you
I almost wanna do this in real life just to see if that's, you know what I mean? I mean, I'm sure it works out to be the same, but it's just,
We used to do ballistic pendulum problems all the time in physics lab.
like you'd actually take a gun and shoot something,
Yeah,
like a real gun, like bring it.
BB guns.
Oh, okay. I was like, boy, you guys are playing cowboys and Indians in school back in the day, that must have been.
Yeah, but when all of a sudden we got lots of international students that had never fired a weapon, it became too dangerous.
Oh, okay.
Yep. Yep. We used to have BB guns and fired BB guns. There is actually a device. There's a ballistic pendulum apparatus that people have used too. All right. So we're going to take a car here. I'm going to set this up just to show you where we're headed. We're not going to complete this one entirely. Partially because you don't have to. I think this is because this was one that was a two-part kind of question. So I'm going to start with a truck here. And it's going to be traveling at 8.33 meters per second. It has a mass of that right there. It's going to come up on a little sportier car. And it's traveling at 2.78 meters per second. It has a mass and this is the situation before. And we're told after that the velocity of the truck and the velocity of the car is 4.167 meters per second relative to the truck. So the problem says that. What that means is the velocity of the car is equal to 4.167 plus the velocity of the truck. And we want to determine our coefficient of elasticity for this problem. So the first thing I got to do is I got to kind of think through what that coefficient is going to look like. And that's going to be the velocity of the car after minus the velocity of the truck after. And if I look at how that problem is set up, oh, well, looky here. And this is the after is equal to 4.167. We know what those are, so I get 4.167 divided by 8.33 minus 0.75. All I have to do. But we can play with a couple of things just to kind of do grins and giggles. I can look at my momentum before and momentum after. So momentum of the truck before, velocity of the truck before, plus the momentum of the car, velocity of the car is going to equal the momentum of the truck, velocity of the truck after, plus the momentum of the car, velocity of the car after. Here comes some fun parts. If I leave it in the terms of these kinds of units, those, life not easy, I end up with 47 point, as we know, the truck, or velocity of the car, now you can go ahead and calculate it if you want to. Because then you can solve for VT and get there. Okay, I'm going to come back to that problem. We've got a sloped wall, and that's 60 degrees. This is going to be 5 feet. We're going to send off a ball at 75 feet per second. This is 45 degrees. It's going to travel with projectile motion, and it's going to hit the wall, and it's going to hit the wall at a point B. The distance between that spot and that spot is 100 feet. The ball is going to rebound and hit at some point C. We're only going to worry about this situation at point B. But that's the whole idea. The ball it's a 2.2 pound ball. And we're given that E is equal to 0.5. We want to find the velocity of the ball at B when it hits the wall, just after it hits the wall. Good news is I can use change in position is equal to V naught xt. This is going to be my 100 divided by 75 cosine 45 gives me T. T is going to be 1.887 seconds. I can find the velocity B in the y direction. And that's going to equal the velocity initial in the y direction minus gt. That's going to be 75 degrees minus 32.2 times my 1.887 seconds. And this is going to give me a negative 7.684 feet per second. So my velocity vector at B is going to be the 75 cosine 45 degrees in the I direction minus 7.684 in the J direction. And that works out to be like 53 in the I direction. So the magnitude of velocity is going to end up being 53.59, and the angle is like 8.244 degrees. And this is the before situation. We're looking for the after situation.
Dr. Whitlock,
Yeah,
what is the bottom number of that, the tangent?
53.03. It comes from right here.
Oh, okay. Okay, thank you.
Okay, so all of that's the before. So let's look at what's happening on our slope. So I'm going to give myself a normal, okay? There's my normal. This is my 60 degree. This is my horizontal. Okay, that's just a reference point horizontal. Okay, and if that's a 60 degree, right, if I get this part, this ends up being a 60 degree, which means this is a 30 degree. Everybody with me? All right, so now we're going to draw in my velocity vector. And it comes in here, right there, and this is my 8.244 degree spot. -30 minus 8.244 degrees, which is giving me 21.756 degrees. So what happens now is I'm going to have the velocity of the ball in the x direction. And the thing is, we don't necessarily know, if I have it bounce up like this, we don't necessarily know what that angle is. Okay, because it's going to bounce off the wall. We don't know what that angle is. So I'm going to have that, this is the before, and this is going to be the after. So I'm going to end up with my 0.2 divided by my 32.2. And this becomes my 53.59 sine of 21.7560 is going to end up giving me my 0.2 divided by 32, and this is VB prime cosine of my angle going out. That part's all cancel, and I end up with VB cosine of the phi that we're looking for is equal to 19.862. And now my efficiency factor kicks in. Because it's going to give me the y component. So E is equal to 0.5, which is going to give me minus VBY plus my VBY. And this is the prime one minus 0. So I end up with minus VB sine of phi. And this is, because y is in the negative direction, I get my 53.9. I wonder if I wrote something down wrong. I wonder if that should be cosine. I think I just wrote something on my notes wrong. This may be cosine. The number's right. This number's correct, but I may have written it down wrong. Sine of 21.756 degrees. And then you get VB sine of the angle is equal to 24.885. So now I can figure out the tangent of the angle, because I'm going to do my sine over the cosine thing. It's going to give me that the angle is 51.4 degrees. I can go back and solve for VB, and it becomes 31.8 feet per second. All right, I'm going to set up one more, and we're going to take it as far as we can with the theory that we already have. Okay? Because it's going to set us up for what comes next. And why we need to look at what comes next. So I'm going to do a billiard ball situation. So I have a table. We're going to start, this is going to be 2 feet, and this is going to be 3 feet. We're going to start with a ball, and this is ball A. It's going to come in and it's going to hit ball B, and ball B is going to go off in this direction and hit at a point B prime. That's going to be 7 feet away. Once it leaves, ball A is going to track and it's going to hit a ball C. Ball C is going to go off in this direction and hit at a C prime. And at that point, ball A is going to track and hit at this spot, A prime. So this is the track of ball A. So this is B and this is C. We're told that this is 2 feet away, we're told that this is 8 feet away, and we're told that this happens to be 3 feet away. We're told that the initial velocity of A is equal to 10 feet per second. And this is going to be elastic in its collisions. And we want to end up finding the final velocities. Okay? We want to end up finding the final velocities. So let's look at B. We're going to end up at B. We're going to end up with a vector B, and it's going to have a VBX component, and it's going to, or this is a Y component, a VBX component. And I'm going to look at the X components first. So I'm going to start with before and after. So the before is just MVA initial. The after, and this is in the X direction, the after is going to be VBX plus VC. Okay? For the Y, there is no Y before. But I have MBY, and it's going in the negative direction per my picture. And now I have MVAY at the end. In this case, M's are equal. So I'm going to end up with VBY is equal to VAY. And this is and we're going to do the prime here just to keep things straight. So from the first equation, I get VA initial is equal to VBX. Write out the M's. The second one gives me VBY is equal to VAY. because it's an elastic collision, I can now do the 1/2 MVA initial squared is equal to 1/2 MVB squared plus 1/2 MVC squared plus 1/2 MVA prime squared. The 1/2 of the masses all come out, so I get VA initial squared is equal to VB squared plus VC squared plus VA prime squared. But that is just equal to and VB squared is equal to VBX squared plus VBY squared. So now I get VA0 squared is equal to VBX squared plus VBY squared plus VC squared plus VAY squared. Except that one, this is prime, is equal to that. So now I get VBX squared plus 2VBY squared plus C squared. And that's VAO squared. So there's 1, there's 2, there's 3. But I have, this is known. That we don't know. I'm one equation short from figuring this out. Based on the information that I have. I need one more equation. Because I have 1, 2, 3, 4 unknowns, and I only have 3 equations. So I need one more. So if I go back and I look at this, there's something I can use to help me out. Which is where we're going to start on Tuesday.
Wait, you mean, are we off next Monday?
No, we're off. We're Monday. No, we'll start on Monday.
Okay.
Nah, we're not off on Monday.
It was last Monday.
No, we're here on Monday. We won't meet tomorrow so that you guys have a chance to do the test. But we're going to be able to use moments at our 4th equation. You guys good on the phone?